So the question we have from James is the following. If electrons are revolving around the nucleus, why does the momentum run out and they fall into the nucleus? So that's a good question. So I'm going to show you an image that could add to the information. So here, if you look at this image, so this is what we often show when we have a nucleus and we have electrons that are moving around. We have electrons that are going like this, and somehow they are creating ovals like this. Now, if you are in your chemistry class, you most likely have seen an image that looks something like this. So what we have here the nucleus, which is the most dense portion of an atom. And then we have electrons that are orbiting around the center. Now, what's interesting here is you have to keep in mind that, yes, we have in the center positive charges, and yes, we have negative charges on the outside. And your question here is, how come these electrons are not coming and hitting the middle part here? Now, you have to keep in mind that if the electrons were not moving at all, they would be attracted to the nucleus. That's without any doubts. But the electrons are going almost close to the speed of light. So they are going straight as long as nothing gets in their way. So they always want to go straight and they have a lot of force, but because they are going straight, but we have in the nucleus here opposite charges, the electrons want to go straight, but then is called back. Want to go straight and it's called back. And want to go straight and then it's called back. Want to go straight and then it comes back. So the idea here is the speed of the electrons makes it that they want to escape the nucleus. However, the charges are there to keep them to come in. Now, some of you would say, well, how come when they come back, they don't reach the middle part? Well, that's a good question. Let's see if I can have an analogy. So you may have seen the solar system with the sun in the middle, with most of the mass in our solar system. And then we have planets that are going all around. And you would say, how come Mercury and Venus and Earth are not collapsing into the sun? Well, that's a good question. Because the planets here want to move straight, they have momentum, they have speed. As they want to go straight, they're called back. They want to go straight, they're called back. So basically, they have here circular or almost circular orbits. So this is very similar in analogy with this one here. In an atom, we're not talking about gravity. We're talking about the fact that because the charges are different and because of the law of attractions, opposite charges want to get closer. So this is what you will learn in grade 9, if I remember well. When your atom is small, that means that you have a small number of protons and you have a fewer number of electrons. So that goes, it's about right for elements all the way to element 20, like calcium. They all have their place around the nucleus. Now, if you look here in grade 11 and 12, you will learn about orbitals. So what are orbitals? So here you could see that if you have here a circle, so in the center here, you have your nucleus, and then you have the electrons all around. But here you could see that the layers, in the circle layers here and the circle layers there, they are not a fine line. And the reason for that is, as you mentioned, electrons here, they're not going on a perfect orbit. They are zigzagging as they are going along. So as I mentioned earlier, we have this one here. It goes straight, and because it goes straight, it's called back by the nucleus, but it doesn't come back right here on this line. It will come back in a little bit more, but the speed will want to make it continue. So the electrons are zigzagging all around the nucleus. And that gives us what we have, these bands of where electrons would be. Now you're going to see, how come there's so many different ones here? Is that as we are getting bigger and bigger atoms, as we are getting more and more protons, there's more and more electrons around. But electrons don't like to be close to each other. So they are making room, they are increasing in diameter because they need to go in different places. So here, when we have these, what we call orbitals, they're like statistical representation of where the electrons are. So you could see they look like clouds, and here you have the layers. It's not a perfect line where the electrons are always there. It is where we have the most chance to find the electrons. So I'm going a bit beyond there, but that's more or less what it is. I'm not sure the proportion. I think it's something like this is the chance of getting the position of the electrons 90% of the time. So here, as you can see, it's not a perfect science. So if you're in grade 9, you're going to say, oh, it's way too much for my brain. Now, if you're in grade 9, the only thing you need to think about are the nucleus and the orbitals. But here, you're right. Electrons are going in circle. They're going to the speed of light, and they want to escape because they go straight, but they are attracted. So here, it is a matter of statistics. And now here we're adding math to chemistry, which is a beauty. And you're going to see how come we know that it looks something like this is that depending on how many electrons we have, depending on the statistic positioning of the electrons, that dictates how different atoms will interact with each other, how we can create different matter. So you have hydrogen and carbon and oxygen. How can we create plastic out of that? Well, we need to arrange the atoms together to create something bigger. And this is influenced by what we call orbitals. So as I mentioned, it's a bit more complicated than grade 9 or grade 10, but it is a great field of study. Because what's interesting, if you like particle physics or you like science, what's interesting with electrons is because they're moving so fast, you can take, for example, sometimes pictures and try to figure out where they are. So you can, when you take a picture, figure out where the charge is. That's something we can do. But once we know the position, there's no way for us to know how fast they're going. For the same reason, if you are taking a picture of a car moving on a highway, you take a picture, you can see the car. But on the picture, it doesn't tell you how fast they're going. So that's something to have. However, if you are taking a video of a car moving, you take a video, you can see the car moving, but you never know exactly where exactly the car is because it's on the movie, on the small video. The car has a speed that is different, and it's hard to pinpoint the position. So if you continue in grade 11 and 12 and even beyond, the electrons are amazing, but because of their speed, it's very hard to study them. And hence, we have this idea of orbitals or high energy electrons around nucleus. And this is part of the next step you can study if you are interested. So I'm not sure if that is answering your question. So I went from an analogy between an atom and the solar system and showing you how in a perfect world, that is true that in grade 9, we know where electrons are, but it's a little bit more intense with what's happening because electrons are always moving. So your question, let's put it up, is why some orbitals can only fill 2 and 6 instead of 8? So if you think of oxygen has 8 protons and 8 neutrons. Because it has 8 protons, it has 8 electrons. Okay, so it will be okay. So here, oxygen, we have 8 protons, so 2 on the first layer and 6 will go on the next layer. What I was mentioning when I give my example of the Michigan Stadium, there we go. What's interesting here is that if you think of the stadium and the M here is where the proton is. So if the proton is right here, that means that electrons are all around. Let's say that there's 100 protons in the middle. That means that you would like to have 100 electrons as close as possible. As the analogy, if you have a game here at the stadium and you have 20,000 spectators, you cannot have 20,000 spectators around the first 5 rows. It's impossible. They cannot all fit. Try to put 100 people on one seat, people will start fighting because they will be upset because they wanted that seat. So what happens? The stadium here has maybe the first 5 rows are the most expensive tickets. And then if more people are coming, they will go in taking tickets further and further away from the main field. The reason, if you've got 20,000 people to sit, you cannot all put them on the first row. So if you think of let's see, where are we? So if you think of an atom like this, we have 4 protons. That means we have 4 electrons. So that means that if you say, well, let's put all the electrons on the same level, quickly there'll be an interaction between the 4 electrons. They don't like to be close to each other, so 2 will be able to stay and other 2 will have to be moving to the next layer. The next layer because they're still attracted by the nucleus, but they're far enough, but they're not in the way of the first 2 here. Now keep in mind that it's possible that one electron can come closer and bump electrons out. It's very, very possible. So if you go back here to my second drawing, if you have magnesium with 12 protons, 2 goes on the first layer, and then you won't put 12 electrons on the first layer. 2 goes on the first layer, then competition happens, 8 will go on the second level, and then if there's more than 2, because here we have 12, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the last 2 will have to go 1 layer above, because you already have 2 electrons competing and winning on this layer. You have 8 electrons competing and winning on this level, and then you have those that will be on the outer levels. And these, if we give them a little bit of energy, they can pop out and go somewhere else. And that will be part of your next chemistry lesson, I'm sure. And I hope that is changing that. And your second part was about the velocity, taking 2 pictures simultaneously. Okay, so what I was doing here is that if you have, let's say you're on a highway, you're on a bridge, you take a picture, you can see the car at one spot. If you have 2 cameras, you could say, okay, I'm going to take a picture, and then 1 second later, I will take another picture, and then I can figure out the speed of the car because I can see them on the highway. Now, if you were to do that with a plane, and you see a plane coming, and you say, oh, I'm going to take a picture, and then the next person takes a picture, if the plane goes at 1,000 kilometers an hour, by the time you take a picture, the plane could have passed you by. So it would be harder for that. But if you think of electrons that are going close to the speed of light, when you see an electron right there and you plan to take a picture, that electron is already at so fast. I think it's, so it's 3 times, so it is 300 million meters per second. By the time you think you see the electrons has passed, the next person can't figure out where it is. So you can't picture the same electrons. So usually we do simulations to figure out what is happening. Now, with AI, it's very possible that you might be able to figure out, okay, let's see if we can take pictures very quickly. That's a good question. But because it's hard to know which one you've taken, the whole idea here is researchers are taking pictures and they figure out, okay, what are we seeing? And electrons going at the speed of light, that's a challenge for that. So all we can do is create, as I showed earlier, is to create, the only thing we can do is create charts where, statistically speaking, where would be the electrons at 90% of the chance. And as I mentioned, it will be something you might study in grade 11, 12, or even beyond if you love chemistry. And the organization of these, we call them orbitals, as I mentioned, dictates how different molecules and how different matter gets together to create new substances. So it's always fun to think about. If you've enjoyed this video, please do a thumbs up. If you have any clarification questions, put them in the comments below. I always read them, and I use your comments to answer them indeed and find some ideas for videos as we come along. On this, I'm going to put here a link to another video, and I'll see you there.